All right. Okay, let's settle in and get started here. So we have two amazing sets of guest lecturers today that I'm super excited about, and it is my pleasure to introduce them both today. So first we'll start off with Dr. Doug Eck, who's the Senior Research Director at Google DeepMind. And there, Doug is overseeing all of Google DeepMind's efforts in generative AI for media, including image generation, music generation, and more. And he has done really, really seminal work in developing music recommendation and music generation systems, and comes from a storied history and training and pedigree in sequence modeling. So I think this should be a really exciting and fun talk. And please join me in welcoming Doug.
Thanks. Thank you very much, Ava. Yeah, you guys are, I just saw the other Doug Blank, and so we're both state school boys from Indiana University. We played a little bit of Ultimate Frisbee together, and he just dropped up here and says, I'm giving the talk after you. So, like, you have the intersection of Doug and IU and Ultimate in front of you. All right, yeah, my name's Doug Eck, and I'm going to give you a very opinionated and historical overview of generative media. And one reason I'm going to give an opinionated and historical overview is that, quite honestly, probably most of you know as much or more about things like Midjourney and what's happening right now. And I say that not only because you're MIT students or you're MIT faculty or you're Turing Award winners, but because like I occasionally do things for Google where, speaking with like some company's C-suite or something like that. And 5 years ago or 6 years ago, you'd go give this talk, and they wouldn't care about AI, they wouldn't understand it at all. And they would like, the slide that would excite them is the picture of the data center. And they're like, oh, have you seen the data centers? It's like, no, we're doing research in machine learning. Like, we're not doing that. Now you give these talks and they're like, oh, well, blah, 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 RLHF. And I'm like, they just mentioned RLHF and they're like a, CTO of a company. So like it's in the air now. We're all concerned and all thinking about the positives and negatives of large language models, how they impact society, how they impact the economy. And of course, as researchers, how we can improve them, make them better, make them safer. I wanted to talk a little bit about how we got here, and with a focus on generative models for images and a little bit of video, and then my main area, my passion area, which is music. And what you won't see here are lots of equations. It's on you to read the papers. Many of you have, and many of this will be just review for you. Much of this will be just review. So we're going to talk about generative AI, and by this I don't mean Michael Jordan style generative AI, though that's part of it. So we're not necessarily talking about modeling the prior and the posterior in a Bayesian sense, but really generating media, generating useful, ideally useful, controllable media, and doing something interesting and valuable with it. And I'll talk about, I'm outlining here 4 families of generative AI: text to text, text to image, text to video, and text to audio. I'm going to talk about, in some sense, a little bit about all of them, but mostly focus on the image, audio, and video work. Part of that has to do with how we're organized in Google DeepMind, with the Gemini team working really hard on language models, and my team largely uses the Gemini models to do things with media. And so it's just the focus that I'm bringing to the table here, my own personal focus. So part of this, how we got here, the obligatory Moore's Law-like slide, is just we've got more and more and more compute. This one's price performance, so it's really not about, per se, processing speed or flops, it's about cost. But you can see that we're following an exponential curve. This is obviously a log scale plot, and it's a nice straight line up and to the left. And this is part of what's driving the success and the quality of generative models across the board. I really like this plot. I apologize that it ends in 2022 from A Brief History of AI, and this was put out as CC, Creative Commons, so I'm happy to use it. This is actually log scale flops, and you're looking at the models going up and to the right there. Let's zoom in a little bit on some recent models. It's actually quite surprising how much more compute has come to play in training these models. Look at AlexNet, a big breakthrough model that happened in Google Brain, 470 petaflops versus, say, GPT-3 with 314 million petaflops. and Minerva 2.7 billion petaflops. So part of the story here is processing power, and we shouldn't discount that. But there's also a bunch of innovation that happened that goes along with this processing power that I'm much more excited about. For the record, I told you this was an opinionated talk. I'm personally not very excited by the scaling laws because it shows you that it's either it's an exponential or it's like a high power function. So if someone comes to you selling solar panels and they say, if you buy exponentially more solar panels from me, I'll give you linearly more power. You should think twice before you buy those solar panels, right? It's not a good deal. And so let's start with images, and let's talk about where we've come from and where we are. I'm going to dive into some of these models and just talk about them a little bit. But you can see on the upper left is Goodfellow Ian's GAN, generative adversarial models, and on the bottom, this graph stops at 2022 with a model that happens to come from our group, Imagine. That's simply because this particular graph stopped. Obviously, we have Midjourney. We have other models now that are driving the state of the art as well. And I want, especially those of you who weren't doing research at this point in time, really take a look at that image. This image and the work that came from these GANs blew our minds. How many of you were doing research when the GAN stuff happened in 2015? How many of you were at the NeurIPS tutorial where Ian got in a fight with Jürgen? A few of you. Oh, nobody. Really? Wow. I'm getting old. Anyway, this drove machine learning, at least the generative modeling part of machine learning, generated so much interest. But by today's standards, this just isn't that impressive of an image, right? Yet it was 2015. It wasn't that long ago. Pretty quickly, we saw some nice improvements on GANs using deep convolution here. Alec Radford, Luke Metz, and Sumit, all of them have made really great names for themselves as well. This was trained on pictures of bedrooms from a real estate data set. And I remember being blown away by these and saying, oh my God, look at the upper right-hand corner. Focus on the upper right-hand corner. It looks like a bed, and it kind of looks like a window. And maybe it has straight walls at right angles. The fact that this model, this ConvNet, could generate images that had this structure at the time was mind-blowing. These were album covers from the same paper. And I work in music, and so I thought, wow, this one looks like it's heavy metal. And we actually were playing around with kind of matching the album covers with music. Some of them have a heavy metal vibe, et cetera, et cetera. A lot of fun. And then, quality starts going up pretty quickly, right? This was StyleGAN, 2018. I think this is when generative imagery started to hit the press. What was that website? This is not a face. This is, yeah. And these are, quite impressive, though I would point out many people, maybe it's just those of us that work in the field, I think you can kind of recognize that these are fake now. You can kind of feel it. Some of them are pretty obvious, like the, well, I won't pick on any of these fake people, but I think some of them look, I think some of them look weird, So the artifacts are there, and over time we become more and more resilient to the fakery, if you will, but very, very impressive work. And then 2021, DALL-E comes out of OpenAI. This is from their paper. It is something like the prompt was like walnuts cracked open, right? And the impressive bit here is not the quality of the image. It's that you can type a prompt like walnuts cracked open, and you get it. And don't underestimate the power of that, how important that is. You could try to take a StyleGAN, and if you train it on a diverse data set, you might have pictures of walnuts being cracked open. You won't find it, or it could take you years to find it. You browse around the latent space, that's all you can do, right? So the real breakthrough that made these models useful was not the quality of the images. It was the ability to follow human intent, and I'll come back to that point over and over again. It's the ability to control these models with a prompt that makes them of a perhaps lasting value, but certainly transitory value over the last few years, because we spent a lot of time playing with image generation models. And then I pulled something from 2022 Imagen from our group. Again, somewhat laziness. I thought about grabbing some Midjourney slides, and I didn't know if I could clear them, and blah, blah, blah. And you can all go look at them on your own, and they're amazing, right? But here we are. Here's the punchline slide. The punchline slide is 2015 to 2022. That's 7 years, right? In terms of visible progress in machine learning, I'm hard-pressed to find another 7 years that has brought this kind of hill-climbing improvement on some basic ideas. And I think as those of you that are students right now and you're launching your careers, take stock of that. That means that a whole bunch of doors that were previously closed are now open. And we likely don't know what those doors are or where they lead. And I find it absolutely inspiring to be in this position where I'm still actively working in the space and this kind of opportunity is here. Let's pivot now to text. Alex Graves, with whom I worked for several years with Jürgen Schmidhuber at IDSIA in Switzerland. We were all working on LSTM. I was a postdoc, and Alex was a PhD student. He stuck with LSTM and started in the early aughts doing, did I say that right? Those the aughts? Yeah, the early aughts. Doing text generation. And maybe I'm easily impressed, but I thought this was really cool at the time. It's trained on Wikipedia. For some range of start rail years as dealing with 161 or 18,950 million USD2 in covert all carbonate functions, I was like, it kind of smells like language. It's not quite random, right? It's got a vibe to it. And you could see, actually I could see that there's a hill to climb here, right? He'd sort of cracked a code with these LSTM experiments in my mind, because I was working on this earlier and we couldn't even get here. And so once you see this kind of progress starting, I think it becomes quite compelling. 2013 to 2019, 6 years later, the famous GPT-2 that came from Transformer. I worked closely with the Transformer folks while they were still at Google. Really impressed by that paper. Now, here's a prompt written by a human that talks about a herd of unicorns. We look 4 or 5 paragraphs down in the text, and wow, it's still talking about unicorns. Like at the time, that's just also shockingly impressive. And I think this example, comparing Alex's work with recurrent neural networks and this transformer approach, this makes the point, right? If attention is good for anything, any one thing, it is that it can trivially attend to something in the deep past if it needs to and use it. It doesn't need to use a recurrent memory to try to bring forward in time this dynamic state and then unpack that state. And it could just as easily look at stuff in the distant past as now. I'll come back to that. But I want to dive into, this is sort of a 2 or 3 part talk, hopefully leaving time for questions. I want to go a little bit deeper into some of the image generation technologies. For those of you that are looking for a really deep dive, you're not going to get that here today. But that's okay too. There's lots of time to read papers. So I'm going to dive into 2 models that came from our group. My reason for focusing on these models is that one of them on the left, Imagine, is based on diffusion, and one of them on the right, Parti, is an LLM all the way through. And I think it's instructive to see how both of these approaches can work quite well and have relative weaknesses and relative strengths. And I think a lot of work in building usable, fast, controllable image generation models is actually going to come from pulling from numerous families like this and using them when they make sense. So let's start with Imagine. This landed just in time for NeurIPS in 2020. Is that right? No. 2020, yeah. We'll come back to it. I should have that date memorized. You know what? And now I'm embarrassed. 2022. Okay. And so what this model is doing is taking advantage of diffusion, a process that nature has known about since the beginning of time, that was brought into machine learning. Probably the first person to do this was Joshua Soldikstein in a paper when he was still at Stanford, using diffusion for training models. He worked with us for about 8 years at Google, reported to me until recently, and is now at Anthropic. I'm really thrilled for him. I think he's going to do great work there. So what's this diffusion process? If you haven't looked at it in your coursework, it's a really cool trick. The idea is we're going to learn some sort of mathematical destructive process that slowly makes noise from structure. So we have a puppy dog on the left, that's structure, and we have noise on the right, some Gaussian noise on the right, and we're going to learn some way to gradually turn the puppy dog into noise, and the puppy dog disappears and the noise takes over. Of course, the crucial trick, for those of you that know the model, is that this is done in a fashion that's invertible. And because it's invertible, we can run it backwards. And running it backwards is quite cool, because now we can go from noise to puppy dogs in multiple steps. And then furthermore, we can collapse these multiple steps. The underlying process would be hundreds or thousands of tiny steps. We can collapse that by learning that mapping, that invertible mapping with a neural network, into 1, 2, or 3, or 4, or 5 steps. And this gives us this wonderful back and forth process. It also has the property of being non-causal. So there's no autoregressive component, meaning it parallelizes quite well. And it's also quite good at picking up global structure in images. So it's quite well suited for image generation. And specifically, Imagine, which for a short time was at the state of the art, it was the best model in the world. Things progress. We're all still working on these things. Takes text as an input and outputs 1024 by 1024 pixels by going through three steps. One, to make a very low resolution image, 64 by 64. Think Ian Goodfellow's generated face. And actually, I think that might have been 28 by 28. And then continually upsampling with more and more parameters. And so it looks like this. We have a prompt from a user, a photo of a group of teddy bears eating pizza in Times Square. And that gets run through some sort of pre-trained model. No learning is happening on the language model. It's off the shelf. It gives us some vector. That vector is a bunch of numbers that represent that string. And then that embedding, that vector, is used to condition the noise to start generating an image. And then that embedding is kept there, and the low-res image replaces noise and is used to create a higher-res image, which replaces noise and is used to create a higher-res image. The embedding is always there, pinning the model down so that it generates what you want. And critically, and very interestingly, for those of you that like to build cool things, you're not really required to use the same embedding each time. There's no reason why you have to use the same embedding each time. And it turns out that's one of the great ways to use diffusion to do style transfer. You can start with an embedding that's talking about a photo of a group of teddy bears, and in the last phase, you can say, oh, screw that, I want this to look like Picasso. And you put a Picasso embedding in there, and it will obey it to some extent. And it will thus style transfer the result, which I think is kind of cool. So that's one family of models. Another family of models that I wanted to talk about is autoregressive models all the way through. So we're not going to use diffusion. We're instead going to output a series of tokens that become an image, particular kind of decoder that is driven directly by tokens. So you have a transformer encoder and a transformer decoder. You inject the text into the process, a dignified beaver wearing glasses, etc. By the way, there's this whole era, like it's going to be of a time when everybody was kind of worried about the impact of these models, where they're like choosing the safest and stupidest prompts in the world, right? Like the dignified beaver, or like the astronaut on a horse in outer space, or like the turtles. I don't know. It's of an era. Like I think we're going to remember that as, oh, no one wanted to like really get in trouble by generating cool things. They want to generate animals wearing suits, So we have fundamentally the same outcome here. We have an image that's conditioned on text, but we have a very different way of generating the actual pixels. In this case, the decoding is being handled by a language model. In the case of Imagine, the decoding is being handled by a diffusion model. And I think kind of beyond that, it doesn't really matter. What's critical for me here, and where I think the revolution has happened, my personal opinion, it's in that little arrow that's driving the text into the model. It's the fact that there's human control. It's the second time I've focused on that. This model can be driven by text strings and other conditioning methods, and the images will reflect that intent. Nice scaling slide. I really like the Parti paper. I'm not on the paper, so I'm not like patting myself on the back. They did a nice study of just what happens to these images as you add more and more parameters. Not hard work, but nice investigation. And so I really like the bottom one, a green sign that says very deep learning, and is at the edge of the Grand Canyon. If you have 20 billion parameters, you're going to spell deep learning correctly. Very deep learning, it's got it. If you have 350 million parameters on the left, it's just garbage. It's useless, right? This is exactly the same model. It's the same code, okay? So this is just increasing capacity, and you see just the flavor of the images changes pretty dramatically. By the way, this makes it very hard as we move into large-scale models. It makes it really hard to compare models, because even relatively small differences in scale can yield very different outputs. And as scientists, we really want to understand what methods work best. We don't necessarily want to understand what method plus scale works best. I mean, we might if we have a budget, but I think deep down inside we really want the right algorithms in play here. Okay, let's shift from images to video. And I'm going to tell a similar story for video. Again, these are the same slightly out-of-date slides. And in fact, there's been some really nice recent video work to come out of Runway and also Midjourney. So it's a really, really hot and active space. We remain very active in this space in Google DeepMind. Here you're seeing some images from Imagine, which is, again, this is diffusion-based, and then versus a model called Finaki, which is very similar to Parti in the sense that it's a language model all the way through. And I would comment that even in these slides, you can get a kind of idea of sort of the natural biases of some of these models. The way the diffusion process works, it's moving through, I'll do a slide on this, but it's basically 3D diffusion, so you're diffusing over time as well. And you tend to get really smooth movements. So a lot of the images that you see that look like kind of a picture that you've animated for a couple of seconds, diffusion does that very, very well. And in fact, the folks that are working on this are like, oh, that looks like diffusion, even if we don't know where the model came from. It's kind of got a feel to it. The Finaki stuff, the language modeling stuff, seems to be more able to follow complex prompts and give rise to more complicated movements and be more dynamic at the expense of the quality of an individual frame. Now, these are all conditioned on how big was the model, did you get something wrong? Probably you can do something similar with both, but there's a kind of natural bias towards smooth movements with diffusion and an ability to fuse multiple prompts with language modeling. This is the Imagine stack. Basically, this is just showing you, this is number salad, but in all of the rows 2 and 3, you're seeing 3 numbers. It's the number of frames times width times height. So it's basically defining a column of images that you're making, and we're gradually upsampling both in frame rate and in size. That's all I want to say about Imagine right now. Finaki, there will be a quiz on this slide, memorize it all, please, is basically showing you that there's a bunch of fancy encoding happening that's generating tokens able to capture small patches of image, and then you serialize that, and that's your language model, and then the ability to train and decode into video. But it's basically transformers all the way down. And these open-ended text prompts from Transformer can change over time, can generate video that can be multiple minutes long because it's autoregressive. You can just keep going. And the emphasis really here is on novel combinations of concepts that don't exist in the training set. So the research goals here were not, oh, can I use language models to make something that looks like diffusion? The research goals were more, can I tell a longer story? And this was one of the videos that we released that I thought was pretty cool. It's a balloon stuck in the branches of a redwood tree. These are the actual prompts. Camera pans from the tree with a single balloon to the zoo entrance. Camera pans to the zoo entrance. Camera moves very quickly into the zoo. First-person view of flying inside a beautiful garden. The head of a giraffe emerges from the side. Giraffe walks towards a tree. Zoom into the giraffe's mouth. Zoom into the giraffe's mouth. Thank you. Et cetera, et cetera. I should get a good David Attenborough reading of this. To give you an idea of why this matters, at least the diffusion models that we've trained natively, I can't say it's not possible, there were some prompts that were surprisingly hard. My favorite prompt was a baby rolls a red ball across the floor, and the ball turns into a bird and flies away. And Finaki's just able to do that, okay? And the diffusion models we had would generate the ball rolling across the floor, generate a cut, and then go to a bird flying in the sky, right? So now part of that might have just been how it was trained. So, if I had someone from the Imagine team, they could raise their hand vigorously and say, yeah, but you're not being fair. We could have done that if we had different training data. Don't get me wrong, you can do it. But there's kind of a natural, smoother progression that seems to be possible with these language models. Finally, I wanted to, in the video space, I wanted to throw in a slide about Dream Fusion, because I think it's cool, and I also think it points to some real challenges in video right now. We've been making experimental videos internally and trying to tell real stories. So try to tell like a 10-minute story by doing multiple cuts and do a script and have some fun. And some of the challenges, you know, there's no secrets here. They're pretty predictable. It's really hard to generate the same room twice if all you're doing is using prompts, right? So you have like a 5-second scene that's set in this auditorium, and you're like, oh no, I want another view. And oh, all right, it's an auditorium with red chairs and blah, 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 because you don't really have any way to bring the same room into multiple cuts. That's true also for characters. And so Dream Fusion, this gives us one direction forward. This is fundamentally having Imogen generate multiple views of the same object, training it to do that, and then using NERF to render those views. So it's quite simple, but it does give rise to real 3D volumes that can be imported into video games, into your favorite 3D modeling software, and is both playful, but I think also points to a fusion between not just NERF and Imagine, which was the fusion they're talking about here, but really video making where you have control over the spaces that you're working in, and also the characters that you're using. Okay, we're okay. A quick aside. This is meant to be a very quick aside. Then we'll get on to my love, which is music. A little robotics. I don't like these. Okay, there we go. So this is coming from Google Robotics, and they started applying language models to the task of robotics. And the task would be something like, hey, robot, I knocked my can of Coke over. Would you go get me another Coke? Okay. And this is home robotics that could help people with certain movement disabilities, et cetera, right? And it turns out that's really hard in robotics. Those of you, anybody here do robotics? This is MIT. Yeah. So none of you were at NeurIPS at the time, but you're all doing robotics. This is perfect. Okay. It's possible it's because like universities like University of Montreal invested in deep learning early, not Yale and Harvard and et cetera. It's meant for a laugh. Come on, give me a break. I'm just joking. I was at University of Montreal for a while. Okay, so there are really four directions of research, but I want to focus on the first one, SEICAN. SEICAN simply takes a phrase like "I spilled my drink, can you help?" and divide and conquers it into a bunch of prompts. So this is like classic. You could use GPT for this. You could use Bard for this. You could use whatever you want. And then that gets merged with this list of affordances that the robot can handle. And you just take the ones that you can merge, and it actually worked really well. It had great lift. And then they went a little bit further, somewhat naively, and just said, well, why don't we just like treat the robot control as a language modeling problem? Let's create a language model for robot control, and then we're just going to train the model to generate the appropriate robot control signals from the command. And it actually worked quite well. This is not a talk for me to give right now. What struck me here, and the reason I brought it up, was not to show off Vincent Van Uyck's robotics stuff at Google, but to point out that this is just another example of taking human intent and using a language model to translate that human intent into another domain. So the way that I read this is that the real power of large language models is not reasoning, it's not AGI, it's that these models speak to us in our language, and they're fundamentally doing translation. But the kind of translation they're doing must be expanded beyond translating from one human language to another. This is translation from human language to robot ease. And image generation is translation from the intent, make me a picture of a beaver wearing a stupid suit, into whatever language you can build around the generation of images, and so on. And I think for me, that's where the revolution lies. And I think to the extent that we can understand that, we'll really be driven in the right direction with respect to what to do with language models. Okay, on to music and audio. Now, this video is private. Oh, you're not? That's not true. I'm still logged in as me. Is that for real? You may not get to hear this, which is it's probably okay. So this is some of the music that I generated in 2002 which now is sadly more than 20 years ago, in Jürgen Schmidhuber's lab doing LSTM. And the reason that we were looking at music was that music repeats. And music has nested structure. And in the world of sequence learning, that's kind of an interesting property. Like even the simplest music, even kids' music, the kind of music that like a 4-year-old might like get, will probably repeat. And if you come from the sequence learning background of recurrent neural networks and that family of models, that's actually really hard. You start to think your brain goes a little crazy, and you start to tell yourself, oh, we need stacks. Oh no, it's context sensitive. Oh no, we can't learn it with a neural network. These sorts of, now heretical ideas. And so this ended up being a very interesting direction of work that I've carried on. I don't think I can play this, which is a little weird, because I know, sign in. All right, verify it's you. Okay. This is how weird we are with security. Like, it signs me out during a talk. Welcome to Google. This is my corp laptop. And let's watch a bunch of slides go by really fast. It'll be fun. And this is where we are. I'm gonna review. All right, everybody gets sick to their stomach a little bit here. Robotics, boom, boom, boom. Close your eyes. My wife's an architect, and we're doing a plan for a house, and she's like, I'm gonna move around the plan for a while. Close your eyes, because it makes you car sick. She's like zooming in and out. This is too much. All right. Whew. Thank God you're gonna get to hear this. This is really good, guys. 2002. I spent so much time writing the code to do this work and training this model. It's an LSTM network, very small, on the order of like 20, 25, cells, very small, trying to learn enough structure to be able to generate some music. This is just MIDI, right? It's just generating note names and they're being rendered. So, yes, it's impressive. I know. I know. It got me a job with Yoshua Bengio at University of Montreal. True story as faculty. This actual paper from meeting him in Switzerland. So, that worked out for me. But really, it was pretty primitive. In fact, these chord changes were fixed. So, that's providing all this structure. Let's not talk further about that. Let's just keep moving a little bit further. But I wanted to show it to you because it was movement. There's another person who did good work in this space, because I think it was good work. I'm being self-deprecating. It was just where we were at the time. A guy named Mike Moser, who does a bunch of work with memory. He's cog-sci in Denver and now at Google. He was also working on using neural networks to do music for the same reason. He's like, I was obsessed with memory. Music is about memory. And he called his model Concert. And my favorite line, because I read his paper when I was doing my dissertation, it's got the most beautiful line. He said, this neural network generates music only its mother could love. It's so good and so true. And so, Okay, so we're moving forward in time. Now we're in 2016. We're still working with MIDI data. And a paper that I thought was a really nice paper by Natasha Jakes, who's from MIT Media Lab. She's now at Washington. We did some stuff with what looks a little bit like RLHF. We didn't call it that. But we're going to now take a neural network and we're going to train it on some external reward that's non-differentiable reward. And in our case, the reward where it's not RLHF, there's no HF, the reward is from a series of basically what we know about the problem. And the paper also looked at chemistry generating molecules in string format. But what we said was, we know a lot about music. How could we show a neural network some of the rules of composition, kind of naively, just to see what would happen? And so, it turns out that we pulled a textbook of counterpoint from the 18th century. And mostly, if those of you that know music, you usually think of counterpoint as how the chords go together in Bach, right? There's also these rules of counterpoint over time. If you begin, don't repeat notes over and over again. Resolve large leaps, which means if you move away from the tonic, in the key of C, the note C is the tonic. If you jump way up, jump back. Stupid rules. But it turns out, if you optimize a model to try to follow those rules by simply giving it scalar reward, I'll give you a positive number if you do this, and also you need an evaluation function that can evaluate your output. Easy. You actually get really different output. So this is the baseline RNN. At the time, we didn't have the memory to use Q-learning at scale, so these are really small neural networks, so they're underfit. But this is just kind of what the model would do without any tutorial learning. It's like this. And that example is good. The model learned to play sparsely. It learned to just play a few notes. If you listen to a lot of examples, it's kind of, it's just wandery kind of in-key music. With the learning in place, my read is that it actually just starts sounding what I would just call catchy, which is maybe not a surprise. Like you follow the rules, you get catchy. Oops, we'll get catchy. And when we rated these, listeners really liked the tutorial learning, and we just moved on. Interesting little paper I want to show you. So there we are. And then about the same time, 2017 to 2018, we started to look at variational autoencoders and music that can move smoothly from one space to another. In the interest of time, I'm going to skip this demo, but you can see visually the model's able to move smoothly through a latent space, but this latent space is now measures of music, and you're able to move from one place to another. It actually sounds quite nice, and there's some nice musical moments here where it moves nicely from one to another. And then I think this paper I'm quite proud of. This is Music Transformer. The first author on this is Anna Huang, and she's coming here as faculty. And this was really the first paper to use Transformer in this space. And there was a previous paper that we did. So this is part of a project that I started in 2015 called Magenta, which is a project that's about using generative models to make music and art, mostly music. And we wanted to start a project that would help us explore that space. That project has the, the benefit of at least being there early. I don't know if we were successful, but we were there, right? In 2015, we're there, like saying this stuff matters. And trying to do it in a relatively safe space. So language models are kind of intrinsically dangerous because they generate language, and language is about all sorts of ideas. Our music models might bore you, but they're probably not going to lead immediately to Goodwin's Law and some sort of strange, horrible outcome. Anyway, this was trained on Transformer, using a Transformer model. The data is of interest. Data is everything, we know that. We figured out how to take a solo piano performance. Solo, I don't mean one note, but just one person playing the piano, and find the note onsets and their velocities, their loudness, with like 10 millisecond timing. And we ran it on millions of songs in YouTube, pieces of music in YouTube, the ones that we're allowed to look at. And there we were able to just generate lots and lots of MIDI files that had natural expressive timing, and we put that out on open source. So even though we had access to the YouTube stuff, they're out there still. And then we trained this music transformer model on it, and the second trick is that we're getting this like 10 millisecond level timing, like the little bit of a lilt in a waltz, that kind of feel, right? And a couple people on the team, Ian Simon is the main person, figured out that you don't sample time regularly. If you want 10 milliseconds timing, you don't generate an event 100 times a second. You use events to control the clock. So we had some softmax values that were saying, how much do you advance the clock before you make your next note? And then you generate a note and you change the loudness. And so now, if you play a slow major scale, you're generating dozens of events, not thousands of events. That makes it much easier. The other reason I want to show you this is I think it'll teach you something about transformers. You all know everything there is to know about transformers because it's all we talk about in machine learning these days, right? Just about. But someone on this was Monica Danilescu and Anna had this idea of showing the attention mechanism using little colored arcs. So you're going to hear a piece of music generated by music transformer. It's just MIDI, so it's just note events. The piano sounds are being generated by a piece of software. But you're going to be able to see how what the model's attending to. There are 8 attention heads in this particular model. Each one's colored. And I want you to pay attention to when the music repeats. And you can see visually in this timeline, this is the music notes unfolding from time 0 to time end, left to right. You see those little short bursts? Those are fast runs, and they actually are repetitions of a theme. And what you'll see is that the model is locking into the previous version of that theme and repeating it with modification. So give us a look. I think it's quite interesting to see. And also, I stopped in the middle. This is good, because there's a little bit of repetition happening here. This is what's happening in transformer models, presumably for language as well. This just has such strict repetition that it's easy to see. It's attending to the important chunks of information in the past. It can attend into the distant past as easily into the recent past. There's no need to carry along a recurrent memory. For whatever reason, if you look at the very left-hand side here, we noticed in every one of these that we visualized that the transformer was naturally assigning one attention head to keep track of time zero. I can't explain why. It could be a weird side effect of our implementation, but it's quite interesting. It gives it one bit of like absolute time, like how far into the future have I gone, right? And so, you know, there's your, I think, quite cool visualization of what attention is up to. Moving on. So I want to fast forward a bit. Now we're living in the age of audio. Lots of amazing work happening in audio. Sound like Donald Trump. Lots of amazing work happening in audio. The best audio. It's so sad. How did I even let him get into my brain? Project that we've published, and we also have tools out that you can play with called Music LM, which is based upon, I think, a really cool idea of an audio codec that's a language model, so SoundStream. This all came from Google research. So you have an encoder-decoder codec that will basically take any piece of audio and turn it into a sequence of tokens. Those tokens represent tiny slices of audio, and then a trained decoder can take the token stream causally autoregressively and then render it as audio. And the quality is actually quite good. One of the wins here was having a GAN-like real versus fake discriminator loss that helped clean things up. And then using that for music, then conditioning it with something that looks a little bit like the clip embeddings that are used for image generation. So you have an embedding that can generate a vector that aligns rock song with distorted guitar, in this case, with the audio. And so now you have a way to control things. And so here's a little example of this model just continuing on autoregressively on a prompt. So just think of this like any other prompt, but it's music instead of language. So the dotted line is where it becomes generated. Now you can probably hear that there's it sounds a bit compressed, maybe not the highest bit rate. But one of the nice things about a model like Music LM with SoundStream is that we know we can scale this. You know, you basically just increase your vocabulary size to cover finer and finer grained structure of audio, and you just turn the crank, and it just works. So we know we can get to 44 kilohertz stereo and play with all of that. It's just a question of model size. So we really want this expressivity. The other cool model that I wanted to mention that I think is cool is, remember I told you that you can like condition on different things in clever ways? In this case, the training data is source separated, meaning we pull out the drums and the bass and et cetera into separate lines. This can be just done with off-the-shelf software, or you can learn it. And then we condition on one of them. So we pull the vocals out, and then we condition the generation of the other streams with the vocals, right? That means you don't have to give the model the vocals that it was trained on. You can give it your own vocals. So here's one. This is an amateur vocalist with a little bit of reverb singing something. I think it's an amateur vocalist.
When it's all over,
No, it's a professional vocalist.
when we are remain, oh, how do I know that we're all still the same?
And Sing Song will then provide the accompaniment.
When it's all over, when we are remain, oh, how do I know that?
Sorry, I want to keep moving. So this actually, we've played with this model with numbers, lots of musicians, and it's quite addictive. And I think this is where I see us going with this space. It's not just improving the research, but actually building out cool, like new ways for people to express themselves. Okay, couple of thoughts about control and safety, and then we're done. This is a picture of an avalanche, and it's my personal analogy for what the future of work might look like, and I think it's quite serious. So I make a lot of jokes, but I take this part of the talk really seriously. We could see pretty big changes coming in how work is structured based upon the automation that we're getting from large language models. And this also hits the arts, also hits the creative fields. And the analogy that I came up with when I talk, for example, I think this analogy is a little simple for the MIT group, but you're all MIT, so you're really smart. But it's really great for talking to creatives. And it's like an avalanche in the following way, what's happening right now. If there's an avalanche in the mountains on Wednesday, if you're hiking in those mountains on Tuesday, you're fine, right? And really, if you're hiking in those mountains on Thursday, you're probably okay too, just look out for all of the debris. But if you're in those mountains on Wednesday, look out. And the point being made here is if you're mid-career or late career right now in these areas that are going to be disrupted, you have to look out. And history shows that these technical revolutions come at a regular cadence, and they're constantly creating this kind of rethinking of our economy. And so, the reason I use the analogy of avalanches is that the avalanche survival recommendations are not terrible advice in this case. It's kind of corny, I admit. But, if you're caught in an avalanche, you're supposed to kind of swim, try to stay above the snow. At all costs, just keep your head above water or above the snow. Because once that avalanche stops, it's gonna freeze like concrete. So you don't just passively ride out an avalanche if you want to live through it. And the reason I mention that is I think even if people aren't natively curious in this technology, if you're in the creative space, you just learn about it. Just lean into it as much as you can. Because what's going to happen is if this technology is of any use, it's going to give rise to new forms of art, new forms of thinking about things. And there's no reason for you necessarily to get caught in that. I liked this photo that I found on Wikipedia. It's of a woman who exists, Norma Talmadge, and she was unable to adapt to what we call talkies. That was the term for movies with sound. She was very expressive. She was very able to work in silent film, and she was unable to use her voice correctly such that it made sense with microphones. And so her career was really impacted by this. And we don't look back now and say, oh, how horrible it is that we have sound in films. But actually, at a point in time, that was very disruptive to someone's life. And so, I want to both show how serious this is, but also show how it's not necessarily long-term bad. Also, in terms of safety, obviously, we have huge responsibility to avoid things like the recent claims by Stanford researchers that Leon 5B includes child sexual abuse imagery. Completely unacceptable. We have to work through that and understand better ways to red team and make sure data is clean. And also, I'm not trying to pick on the competition. This Midjourney's clearly training on, commercial movies, and I think that's questionable. And we have to really think about a way to control rights, control who are the stakeholders. Someone animated this Avengers film or did the CGI for it, and if I did that work, I think I'd be a little bit annoyed that it's not an exact copy, but it's really close, right? So we have to figure out a way to build a marketplace around creative content. There are precedents for this. One of my favorite is sampling of audio in music, initially hip hop. Biz Markie famously got in trouble for doing this, and the labels just tried to sue it out of existence. Eventually, a piece was made. There's a marketplace for it. You can license samples. You can do sampling, and the people that generated the samples will get paid. And I think that's the outcome we would be looking for here if we can understand, attribution correctly and be honest about where things are going. We do take this seriously at Google, and I always highlight that, you should expect from a company of our size and Microsoft that we have to take this stuff seriously, right? We're very heavily incentivized to do it if you want to set altruism aside or just that, hey, we're good people. But, it's the brand. We need the brand to be trusted. We need trust. And so we're working really hard without any haha, we're going to get away with this. We're working really hard to build products that are safe and to be respectful to our stakeholders. This including, for example, it's not just, I'm going to write a list of 7 things. This is a graph of how you might, Music LM actually, is trying to generate audio. You can look at Music LM online. It's called Audio FX. That's how it was branded. Or music FX. I don't know, branding people change the names of things. And we actually query, we filter your query, what you type in, for hate speech. Only if it gets through that query system is audio generated. Then we try to remove infringing outputs, et cetera, and we're always listening to user feedback along the way. We have some papers. Finally, this is really my closer, but is it art? The answer is yes, but I can say it longer. I think that this is deeply what we're trying to address with Magenta. I'd really encourage you to go look at Magenta, g.co Magenta. Most of what's there is our blog. Our blog's gone a little quiet, but we're going to pour more energy into it in 2024. It's basically looking at the machine learning as a tool in the creative process. We're not trying to have machines make art. We're trying to have machines help you make art. And I strongly believe it doesn't need to make it easier. So I love these two quotes. Creativity is more than just being different. Anyone can be plain weird. That's easy. What's hard is to be as simple as Bach. Making the simple awesomely simple. That's creativity. Charles Mingus. Edgar Degas, even better. Painting is easy when you don't know how, but very difficult when you do. I think that's deeply true. So what we should be asking is, are there people that are taking AI and actually doing something hard, novel, and of artistic interest? And the answer, I think, is yes. I spent a lot of time looking what this year's generation of artists is doing. I really like the work of Josh Rose. You can find him on Medium, or you can also find him on Instagram. And he has a beautiful essay about boring is the new interesting. And he's expressly trying to generate boring images using image generation. But they're so beautiful, and they tell a story. It's calming, it's meditative. So nothing is happening in these images by design. And he talks quite nicely about how AI helps his process. I also really like the work of Beth Fry. She is doing a bunch of what I would call hitting at the uncanny valley, kind of creepily human and non-human at the same time. And it's about body imagery. And as a woman, her experience with the image of her body and how she's playing with food and her body image in ways that I think are really, really both creepy, but also beautiful and expressive. And so I'm hopeful for the future. I'm excited about where we are. And I'm not going to read this quote, but as we move to questions, this is Brian Eno. You should read that, and I'll stop there. I fear I ran a little long. Apologies.
No problem at all. Thank you so much, Doug. Okay, so we have some time for some questions, and then we'll transition towards the next talk for the second half of the class. So any questions first? Yes. I'll bring the mic around.
Thank you so much for the presentation. I have two questions. So first is, why did you leave Montreal to go to Google? Why that transition from being a professor to your role now? And then the second is, I think something in this class that we really talked about is how having more data is really what is driving a lot of AI right now. How long do you think that's going to last? What is the next big, technical revolution? Is it forever just going to be more and more data, in your opinion?
If I told you that, no. So the first answer, why did I leave University of Montreal? The shallow answer is the weather, which is not, that's part of the answer. But I got tenure, and I was on my tenure break, and I just really wanted to do something new. I had been a postdoc for 3 years and faculty for 7 years, and that's a decade. And you add 4 years of grad school, and that's 14 years. And I had the chance to come to Google and be a research scientist, so I didn't stop doing research. And my H index went up. So I didn't stop caring about research. I just had the chance to do something different. And I loved being a professor. And I loved working at Google. So for me, it's a win-win. I don't have a strong value judgment either way, but I was just ready for a change. And then the second one is, it's really not more data, it's data quality and understanding how to align the data sets that you need to solve the problem you want to solve. So if you look at what, one of the things that's kind of cool about Midjourney, I mention them because they're in the zeitgeist right now. Their images are so cinematic. It's almost like Midjourney has its own style, and we're following that style. And so you think, okay, the data, if you want to live in this space, and now the models are actually changing our tastes, right? then we have to be thinking about how to train models that have that similar look and feel. And that's where the art of getting the right data, the right kinds of annotations, it's everything. But I don't think it's more data. I used to think it was like, just give me, I'll take a lot of noisy data over a small amount of clean data. For some definition of small, I don't believe that anymore. I think clean, well thought out, appropriate data is important. I hope, like I've got a bunch of people working on my team, myself included, we don't want to spend the rest of our lives scaling transformer models. And I'm hoping to see more breakthroughs. We've had RLHF, we had pre-training, there's got to be more out there. I mean, our team put out transformer, but please beat it, like do something new so we can have some fun with something new. And I don't think we're done innovating in the space of computer science or in the space of AI/machine learning. So.
Much. I have a question. Who is the owner of the copyrights of the music, which was generated by Magenta?
The person who made the music, so you. We explicitly exercise no copyright, and the data that we trained on we're saying is safe to train on. So it's yours. Good question.
Yeah, I really appreciated the commitment to making safe, actually, like, in the interest of humanity AI. And I was curious what it looks like to try and develop a tool or like some platform where you're the first people in the field, like you invent transformers. How do you anticipate the safety risks that come with them, things like that, when like you're at the cutting edge?
This was a tough question for me. The big difference here is that these things actually work. Like most of what I've done for my 30 years doing like generative AI, this stuff's so bad it's never going to hurt anybody, right? Because it's just bad, right? And then you're left like, wait, actually this generates like really realistic text, right? How do I keep people from being fooled by this? On the music side, we have YouTube. So on our side, we've been thinking about safety and taking down infringing content. So we have a bunch of tooling to rely on. But really, I think the answer is we should just constantly be red teaming ourselves and be humble. And just be aware that we could get this wrong, and we should be thinking really hard about what we launch, and because we only need to screw things up for 3 months to really cause damage, right? So I wish I had we've got this, but we're moving really fast right now. It makes me a little nervous.
Hi. Oh, hi. Thank you. This is about the use of art as a training model. I think for a lot of artists that have been publishing their work online for years, you look 10, 20 years ago and the zeitgeist sort of said, get your work out there, publish it for free, get as many eyes on it as you can. And now a lot of that art is being used to train these models. So for these artists that find themselves in a position where they feel, and not artists that have a copyright like Disney, but the small artists that feel that their work has been used, what would you say to them? Is there a way to put that genie back in the bottle, or?
Yes. Yeah. I think that another really great and very serious question. Thanks for asking it. Rachel Metz, where is she now? Bloomberg? She's a really great tech journalist. She interviewed a woman from Oregon who was an artist. And the tech article was like, artists are infuriated by AI. And you actually listen to what this woman is saying, and she's looking at this output. It was known that her data is in Leon, in the data set. And she's saying, wow, like this is really good, but it looks like my work, doesn't it? And like that's not someone who's enraged, that's someone who's in shock and sad and emotionally affected by this. So it's incredibly serious. I think the genie's out of the bottle right now, but I think we can put it back in. And I think that there has been damage done. And it would be irresponsible to say that there hasn't been damage done. The people that make the art should be paid for the art. Now, as we move forward, we're moving towards having something that looks like robots.txt, which is the text file that's placed at the top level of every website and tells crawlers what they can and can't look at. We will start to see evolving standards for what you might call AI.txt, where you can say, you need to be able to put your art online, and you need to be able to say, hey, this is not for training AI models, right? And you also may have folks that want to be in an ecosystem. So my goal will be twofold. I think we need an AI.txt that's like robots.txt. And then we deeply, deeply, deeply need an ecosystem where people can make money off of this. Like, you pay artists, that helps. Like, y'all got to eat, right? And I think even though our YouTube ecosystem isn't perfect, like, I certainly don't go to parties saying, yoo-hoo, I work with Google, and so we have YouTube, because people get, like, the creator space is challenging sometimes. But the fact is, when people get removed, the biggest complaint about the YouTube creator space is when you get removed from it. And that's kind of a good sign of a marketplace that kind of works. And so, you have this possibility of getting famous, you have the possibility of making some money. I would love for us, and it doesn't have to be Google, just someone, we need to develop some sort of marketplace where you can put your art out there and explicitly say, I want AI-generated outcome from my art, but I want to be paid for it. And it's voluntary. I can be in it or I can be out of it. I think it's possible. By the way, I think it really drives research in attribution and in ways in which we can mix in the style of artists at inference time quickly and efficiently. There's a lot of work to be done. So I think that's how we'd put the genie back in the bottle. It's not going to be just by removing everybody's data. It's going to be by building marketplaces that allow you to have very explicit control over how and when you want your data to be used. And I think there's a lot of money to be made there for someone. I think those marketplaces will evolve. And once they evolve, I think that's going to give us a path forward. We'll still have the equivalent of BitTorrent. There's no reason you have to obey robots.txt. But what happens is, if the marketplace is big enough, and there's enough money moving through it that artists can survive, then what you do is you just kind of put more and more energy into making that marketplace better and better. And that's largely what happened with streaming music services. They're not perfect, but they're better than BitTorrent, right? They're monetizing. It's just you got to figure out the monetization scheme. I know there's a long answer, but I feel strongly about that. So I hope that was helpful.
Awesome. Okay, let's do 2 more questions.
Thank you.
Sorry, Doug.
Sorry. I was interested when you were talking about how it's hard to compare models because the number of parameters will impact the end quality. So I was wondering, how do you compare those models?
So we're working on internally, we do this externally as well, but always having a model card. So the first thing to do is just to pay attention to how many parameters are there. We find, especially if we work even internally with product groups, we have internal competition at Google. Multiple groups are training text-to-image models. Of course they are. And then it's they'll be like, well, the product groups won't notice that this one was trained on 10 times as much data as this one. And so we're moving towards naming models explicitly with the number of parameters and the training data they were trained on. That's thing one. It's just sort of explicitly saying that matters. The data matters. If you're going to compare apples to apples, you have to have roughly the same number of parameters. And you can measure that in compute as opposed to parameters, because what's a parameter? Roughly the same amount of compute is used to do training and inference on these models. And then what's the data set that you used? Then you're getting closer. And I think a lot of it's just good bookkeeping. Beyond that, it's all human evals. And if you actually start using these models, you'll have product goals. You'll have some reason you want to use this model. And that also drives how and when you make a decision of what to use.
Awesome. Okay, last question.
Hi. How do you view this coming avalanche that you talked about impacting software developers, and how specifically can current software developers best prepared? That's question 1. Mm-hmm. Question 2 is, are Google and other big tech companies accounting for this in their current hiring practices, understanding that they might need less developers to accomplish the same productive output?
Yeah, so how is software development going to be impacted? I'm pretty impressed with the code generation that we see right now, right? I certainly see that whether it's ChatGPT or Bard, we're seeing people go there rather than Stack Overflow and other places like that. I had a task that sorry, I'm an old guy. I didn't use any chatbot to solve my last coding problem. I just sort of hacked away at it. But I think it will. Yeah, I think it will make coding less labor intensive, and I think it will long-term change what it means to be a coder, so that you'll have less reward for being able to just hack out tens of thousands of lines of code in your year. If I were to pick an industry where it would really sweep through first, with my limited experience, is the video game industry. I did a year of consulting. I was actually there full-time for a while at Ubisoft in Montreal. It was like a summer, and then turned into part of my sabbatical. And at least at that point in time, so this has been about a decade, maybe some of you in the video game industry, it's the same, it is incredibly labor intensive and incredibly templated and repetitive C++ code, right? It's just it burns them out. Those guys, those people, they're wrist braces and they're going, I'm serious, it's a really, really, it's like the code mines of code mines, the video game industry. In that sense, right? I mean, I think the avalanche. You'll lose. You'll lose a bunch of labor that needs to get done. My hope is that, and my belief is that we won't lose what we love about coding, right? Which is solving hard problems. And what we'll do is we'll do whatever, you have a Xerox machine that solves one problem for you. So the people that used to do the typing in the typing pool do something else. We used to have typing pools, right? So yeah, I think, I do think that there has to be a constriction in the demand for kind of labor-based code. It would be irresponsible to say otherwise. But I don't think, the other way to think about it is like, we also may have just created a whole new sector of the economy around AI. And talk about a non-zero-sum game. If what we do is we close down some options to do, especially very labor-intensive coding, like the kind of video game market that existed for Assassin's Creed or for Doom, but we open up this whole other world where we're chaining together ideas and models and frameworks, and we're solving really complicated problems for people and creating business value, then the people that can do that, call them programmers, call them whatever you want to, they're going to be the kind of people that are in this room that understand the underlying technology. And I think those jobs will spring up. Might even be more. Oh, and the second one.
Because of this new technology?
I don't know. Google's had some limited layoffs over the last 12 months. First, it would be inappropriate for me to comment, but not just because weasel, I don't want to talk about Google, but hey, I don't really know the answer. I'm not a C-suite business person. Companies of the size of Google or Microsoft, we're constantly contracting and expanding. What I see is that the AI market is booming. And this market around the kind of problems that the people that are taking this course are trying to solve is just booming. There's never been growth like I've seen. So you have to offset what might be adjusting and reprioritizing with a genuine concern about, y'all are doing AI, you're going to get jobs, okay? You're going to be fine, right? Right? I mean, that's really my answer. Listen, there's another Doug from Indiana University who should have some time to talk. What are your music examples, huh? Coming soon. Thank you all very much for your attention. And thanks for the questions.